Hey, all. How y'all doing?
Pretty good. How are you?
Doing okay. I appreciate that my headphones are working today. And some of you are thinking, well, dude, you just should have done it differently. You should have set it up differently initially. And yeah, I should have. I didn't know though, and it's working today. And so let's think. Just because I overshare, what the hell? Uh, Another thing to think about for me is a friend of mine just got cancer or just was diagnosed, and my mom died in February. And so, like, compared to those, situations, I'm doing really well. So hopefully your day is going super well because uh, I love it when I'm not dead. Okay, so that's a bummer. Start off that way. Okay, so let's just start off. I'll share a screen and then we'll do some questions that you might have, if you have any questions, that is, related to the administrative things. Then we'll go into questions related to um, any subject matter, and then, like always, new material. Um, One of the thing is I started collecting that yesterday information about, hey, how are the groups working for me? Yes, no. Sometimes it's good, sometimes not so good. Just letting me know sort of information that helps me. Uh, well, great question. So Emma asks, is the sound not working for someone else? Can any of you actually hear me still?
Yeah.
Okay, so I'll reply to Emma. At least some can hear. Maybe Emma's got the same headphones that I have. Um, and certainly, could one of you let her know that if nothing else, the videotape later will have sound on it. Thanks. So there is that thing about the groups, and I love it when groups can work together synchronously at the same time. And so one of the questions is, when would you be free to sort of do that work as a group? And unfortunately, I picked times that weren't perfect relative to, I did a cut and paste of my comparable form, but for the Stat 312, which meets 4 to 5 p.m., I'll still sort of go off of the thing. And if a couple of you are saying, between 9 and 11 p.m. works best for you, maybe that's going to be a natural group, and that would be good. So working with other people at the same time simultaneously is probably best for learning. So please fill out that form. There's a link in the announcements section. Second thing, I think ANOVA's brilliant. We finished it off. Does your understanding still need to improve? Yeah, as you study for exams, yeah, you'll get a better understanding of the analysis of variance method. But speaking of that, there is that sort of exam coming up a week from yesterday. And if you click your way into sample exam one, they should be live by now. So let's verify. Looks better than before. Yeah, there are some questions there. And so by the time we finish up class on Monday, you should feel comfortable with all the content related to your exam for Wednesday. Okay. And then Wednesday of next week is when we're going to spend time going over all of the Q&A from the sample exam to allow y'all to feel comfortable taking the test at some point in time between Wednesday and then Friday night when it's due, Friday night the 3rd. Okay, so I think that's it for administrative things for me, other than next Monday will be a little bit different. That'll happen. Office hours will be later, and then the morning class will be early, like 10 a.m., not noon, like normal. So, any questions about administrative things at all? Okay. How about any subject matter questions? Any subject matter questions? Okay. I guess that means it's time for something new. And if I click my way into week one, Wednesday, Thursday, it seems as though we're switching gears Wednesday into a new topic, regression. So sort of stuff that corresponds to Thursday is regression. And so we're going to do it today, and then finish up Monday of next week. There's a natural breakpoint in the regression problems that will allow you to tackle all the homework related problems from stuff that we'll do in class today. So that's good. And then next Monday, a couple additional things that will be very helpful, but not tied to the homework that's due next week. Okay. So let's first recap where we were at. Chapter 0, the t-test. Are these two means different? Between two groups, are the means different? Last time, ANOVA. Are the means of three groups any of them different from each other, or are they all the same? If I've got five groups, are all five means the same or not? Analysis variance. Let's see if the means differ based on which group you're in. The distinctive change up from ANOVA to regression is now we're saying the mean depends on an X variable in a linear fashion. So rather than just having different groups, the question is, does the mean depend on X? Is there a trend line, if you will? Okay. So a good example for this class, because some of you are from forestry or whatever it's called nowadays. If I tell you the trees DBH and our dioecious trees example in the book, I think there's a problem on that assigned for homework. Can you predict the number of flowers in a tree based on its DBH? Linear maybe makes sense. Or could you predict the age of a tree from its diameter? Okay. If you tell me the species and its diameter at precise, literally, if you're hugging the tree, what is the diameter served between your elbows? Okay. That will tell me maybe the age of the tree. And there's two separate ways that we get to this method called regression. And they're done, one in the late 1800s, early 1900s by Francis Galton, Charles Darwin's cousin, if you didn't happen to know that, because, like, who knows Galton? Galton basically thought there's going to be a relationship genetically, because my cousin's all into the genetics. I should probably get into this business too. My older cousin does genetics. Maybe I should learn about it. He said, taller fathers will tend to have sons that are taller, and shorter fathers will tend to have sons that are shorter. Now, we all know that that's not guaranteed perfectly. Like, every dad that's taller than average isn't necessarily having a son that's taller than average. Sometimes the sons are shorter than average, even if dad is taller than average. My guess is mom is involved in some fashion. Mom might be really short, or there's also natural variability there. But basically, Galton, what he did is he collected data on the heights of 1,048 father-son pairs in France. And we could talk more about that later if you'd like to. But he came up with the picture. And the picture goes something like this. As Galton, Francis Galton, I'm saying let's go with black. I've got height of dad, so father, H height, and son height. Okay. And a collection of individual father-son pairs, 1,048, I believe, were in the data set. And we see a trend. There's some variability, but we see a trend line. And Galton said, you know what? If I say real short dads, shorter than average, right around average, taller than average, tall dads, we're going to have these 1, 2, 3, 4, 5 different groups. And the average height, Y, for the sons of really short dads is there. And for short dads, shorter than average dads, not really short dads, but shorter than average, we could plot the average value for y. And for medium dads, you're going to have then the medium, or I guess the average height of the sons of the medium height dads. And then for the tall dads, but not extremely tall, and then the extremely tall dads, we could graph these means, connect the dots, and lo and behold, it forms a straight line. At least that's what he saw with that one data set. And so Galton sort of comes to this understanding of, oh, look, the trend line predicting the height of a son from the height of the son's father seems pretty linear. Gauss tried the problem a little bit differently back in the day, the early 1800s, I think, with the asteroid Ceres. Actually, a decade before, he came up with the method to, if you're plotting points along a straight line, if you sort of try your best to make it along a perfect straight line, but if it's not perfectly straight, how could you draw the best trend out into the future where that straight line would occur? Um, he basically got the location of an asteroid uh, forwarded to him by I was going to say email, but that's wrong. Mail in Holland. A an astronomer said, "Okay, I see the thing. I see the thing. I see the thing." And he sent off to Gauss the date and time of the observation of the location in the sky, the date, time, and location. So the angle up. Okay. And so from date and time, he gets information about, okay, where things are at. And we see the progression of this asteroid across the sky on consecutive nights, sort of like the moon does. But eventually, it gets towards the end of the cycle, and the sun is coming up and this asteroid is really low in the sky, and this astronomer's like, I can barely see it today, and I only know it's there because I was plotting the straight line across the sky, and it's doing great, yay. But I know tomorrow the sun will completely obscure my ability to see the asteroid at all, but I want to know where it's going to be. So he writes Gauss with all the information about the locations and time and angle in the sky, okay, and says, okay, when should I look in the sky again? And where in the sky should I look? And Gauss looks at the data and says, oh, look, I invented a method 10 years ago that could tackle this problem. Gauss basically mailed back, I was going to say email again. That's what we do these days. Gauss mailed back here's where you look on this particular date. And for the next 2 or 3 days, said, and here's where it will be the day after, and yet again, the day after. And indeed, that's exactly where the thing was. And so that's sort of cool that this method is like 225 years old from one point of view, or 125 years old from a different point of view. But the upshot really is if you tell me an X and a corresponding Y, I could now tackle problems. Let me show you an example data set, and maybe I'll pick the one I really want. Well, different class, different book. Let's see if I could find our class. And an example that at least I've uploaded for you all. Okay, so let's go with oh yeah, let's go corn yield. Um Now I've got this data for a reason that we'll talk about it later in the term that will relate the yield of corn to the amount of rainfall that we get. I don't want to go there just yet. I want to say, is the yield of corn maybe dependent upon the year? And this is corn yield in bushels per acre in one particular county in Illinois. Let's even forget the rainfalls in the data set. Does the yield depend on the year? And for those of you who've taken the crops history class, tractors, you know, irrigation, there's probably some reason why year would be related to yield. Fertilizer, um, combine harvester. So analyze the fit y by x. Tell me how the yield depends on the year, or does yield depend on year? I click OK. And I see a graph drawn in. This is not a clear question. I mean, it's sort of like, is there a relationship? Looks pretty darn flat, doesn't it? If we ignored these 1, 2, 3 data points over here in this corner, it seems really quite flat. But overall, if I were to add in a trend line, and if you ever have a scatter plot, you can fit a trend line predicting y from x. We see here's the best fitting trend line. And on Monday next week, we'll talk about what we mean when we say best fitting trend line. I'll walk you through Gauss's approach and a couple other things. But right now, I'm sort of saying I fit a trend line in. You're looking over here, you see a p-value 0.0187. That seems as though there's a relationship because didn't we learn before a low p-value means there is a trend, a relationship that across the different groups in ANOVA, if they're at least one of them with a different mean, say there's a relationship between which group you're in and then the response on average. Here we're saying there's a relationship between year and yield on average. That's really the question. Is there a relationship between what year it is and the average yield? Is there a trend of sorts? And I'm seeing with this p-value, the answer is going to be, yeah, it looks like. Well, like before with ANOVA, we have to actually have a few assumptions holding validly, if you will, that the assumptions have to be either reasonable to believe or something you take on faith. But if you're willing to believe those things, then you can then do a hypothesis test. So, what I'd love to do is to briefly talk about what the assumptions are in this simple linear regression model. And we'll talk about checking the assumptions later, both in the context of a lab and then also chapters 8 and 9 will focus. So that's a bit later. We'll talk about checking the assumptions. But for now, I want to just sort of highlight the way that these assumptions are working. And I think it's best to do this in the context of an example. And so the example I want to use is like, what if we know y is the weight of a person and X is the height of that person. Now I'm specifying California adult males just to say, well, that's a well-defined group and we see them every day as we walk around. And so the question really is there a relationship between heights and weights? And your gut feeling is, yeah, taller people on average weigh more. Taller people on average seem to weigh more. Let's focus on this first part of the equation. Okay. Beta 0 plus beta 1 times x. If you tell me the height of an individual, x, and if you knew beta 0 and beta 1, both values, then I'm saying that's going to tell you mu y. And this is a term that we may later use, but we're not going to emphasize today. But I'm going to say mu y. Mu means the mean. The mean of what? The mean of y in this case. And it's the mean of y, and it clearly depends on x in a linear fashion. Mu y is just beta 0 plus beta 1 times x. So in other words, if you tell me beta 0 and beta 1, you're going to tell me the typical weight of someone based on their height. You tell me x, their height, and you tell me beta 0 and beta 1, I'm going to tell you what I would estimate the average weight of that person's going to be. And some people are more heavy and some people are lighter, but there's the same average weight based on just their height information alone. I guess the wrinkle here, though, is because this is a stat class and lowercase Greek letters like beta 0 and beta 1 are not known values. Um, we would need to maybe estimate them. Okay. We would need to maybe estimate them. But clearly, If beta 1 is 0, and that's the null hypothesis we have in our test of hypothesis, if beta 1 is 0, it means mu y isn't dependent on x at all. In other words, there's no relationship between heights and weights. If the slope beta 1 is 0, that says there is no relationship between x and y. Okay, quick aside comment. I'm assuming that if there is a relationship between X and Y, that it's a linear relationship in this discussion. Some of you are saying, well, some relationships are actually curved. Okay, fine, you're right. We will later deal with those situations. For now, we're just saying, assuming the only possible relationships are linear, then a test of whether the slope is 0 or not is a test of whether there is a relationship or not. So I want to know really the question, is beta 1 0 or is it something else? Because if beta 1 is something other than 0, you'd say there is a relationship between x and y. If beta 1 is non-zero at all, that says that, well, for a different beta, we would have a different typical y. So that's the first part of what we need to figure out. The second part is this epsilon thing. Okay. Epsilon, we're going to say, well, those are errors around the trend line. It says, how much heavier are you than the average person at your height? My epsilon's positive because I weigh more than the average person does who's 5'8.5", which is my height. I'm a little bit plump. My epsilon is positive. But if we believe the following things to be true, then I could do a hypothesis test. Literally, I have to have normality. I have to have mean 0 on average for the errors around the population trend line. I have to have the same constant standard deviation, and the epsilons have to be independently chosen from each other. Let's rephrase that. If I tell you my epsilon is positive, if you know that I weigh more than average for a person of my height, that doesn't tell you anything about my neighbor David across the street. I mean, literally, if I tell you I'm a little bit heavier than average for someone of my height, have I told you anything about David? No, not at all. And so the epsilons being independent of each other basically say knowing one person's difference from average won't help you predict any other person's difference from average. And if those four things are true, I can literally do everything I need to do. I could literally get a hypothesis test. I can get a p-value like we already emphasized. We could get a conclusion because you all know if your p-value is below 0.05, you believe the alternative hypothesis. If your p-value is above 0.05, you don't. We haven't really talked about the T ratio, our test statistic, just yet. However, any questions on this slide before we talk about the t-test? Okay, so next slide. Okay, so really what we're trying to do today is we're going to talk, well, in the lab, you're going to do a little bit of work checking the regression assumptions. We're going to do this in class or lecture, L for lecture. We're going to talk about that in lecture. Um, And these here will probably be Monday. Okay. So I guess we got two things to do. Let's do it. I'm gonna sort of skip over this and get back to this right before the lab, because this is less important than other parts of the lecture. Same thing there. Let's get into the t-test for the slope. A test, a hypothesis test, we need to have a measure that we call a test statistic. That measure is how close are the data to what we think we should tend to see the data looking like if the null hypothesis were indeed true. If my hypothesis really is that the slope is 0, I need to have some sort of a sample trend line to compare to 0 and see how well I am matching up. My test statistic T, I guess I should rewrite that here. My test statistic T is my sample slope B1 compared to what the null hypothesis says I should be seeing, B1 compared to 0, over, well, the standard error for B1, my sample slope B1, the slope that's best fitting to my data via that least squares approach. How far off could my sample slope be from the truth? That's going to give me my test statistic T. And the key thing I want you to focus on for now is there's an equation for that standard error. And conceptually, I think each of the parts in this equation make sense. Okay. The standard error for the slope, the amount of precision we have in our sample slope around the true underlying population, how well our sample slope measures the population slope, how far off could our sample slope be from the population slope. It seems to relate to n, and that makes sense. Why would n be important? Well, because the larger n is, the more data we have. The more data we have, the more precision we should have in our understanding of y based on x. So more data, more precision, smaller standard errors. Larger n makes sense. This SX in the denominator, that's a little bit tough to grab onto. What about the standard, the spread of the data points around the trend line? Okay, so SE is, if you will, the mean square error, the root mean square error of the errors around the trend line. Let's talk about the role each of these three things would play in our trend line. What I'm going to ask you to do is pretend you're going to the optometrist. And not everyone does this, but I do from time to time because I wear glasses. And the optometrist will, at one point in time, after determining approximately what my prescription will be, the optometrist will show me a pair of things. He'll say, "Okay, how well do you see right now?" And he'll usually do the right eye first. How clearly do you see? Is this better or is this? So the question I have for you is, like the optometrist has the question, which of the following two graphs more clearly allows you to identify the slope? Would it be, okay, so let's go with, would it be with 6 data points? All 6. Or 30? Would you rather have more data or less? Most of you are thinking, well, the answer obviously, duh, is more. But what I'm thinking is, if I drew in a trend line like that, you'd say, it's probably pretty close. But if I drew in that trend line, you'd say, also could be it. Or this one, you'd say, also could be it. So there's a variety of possible true trend lines that could have produced those data. What about this other one? That is pretty clearly really close to the only trend line in the population that could have produced the results, the data that I saw. So you more precisely know the truth in this case. More data is better. We saw that in our equation. Yeah, literally right there. If n goes up, the spread, the standard error, the amount of error in our estimate of the slope should go down. Okay, we're good with there. What about this S sub E? That's a measure of the spread of the data the around the trend line. How far vertically are the data points around the trend line? Literally, if I look at the vertical distances between data points and that trend line, what is the error? So let's show you inside JMP's output. I've got my fun graph here. There is my graph, and let's switch from red to purple. These vertical errors around the trend line are, if you will, a measure of how far off the trend line is from the data. And with a given data set, I guess there's no way we're ever going to be perfect unless all the data points are on a perfectly straight line. But these vertical errors, you could find the standard deviation of them, and I'll just say S sub E is approximately equal to the standard deviation of these vertical errors. If you want me to be more precise, I could be more precise. But I'm thinking if you just think approximately a vertical spread around the trend line, how far off are we? That's a number we call S sub E. So again, back to the optometrist office, I'm going to give you two choices. Would you rather have a small S sub E or a large S sub E? Here are the two choices. Small S sub E right here. 10 data points, all pretty much following a perfectly straight line? Or would you rather have 10 data points with large errors around the population? Large errors around the sample trend line. Okay, so here you're saying very precise. Here, not very precise at all. In which case, are we more precisely fitting the trend? In which case, do you more clearly say, oh, yeah, I know what's going on clearly downstairs? I more clearly know in this second situation that the trend that I fit is going to match up to the underlying population's trend line. Here, this other sample slope or that one could fit darn about as well. So we'd say you're much better off in the second circumstance. Smaller spread around the trend line is better. Smaller SE gives you more precision. What about this SX? The standard deviation of the X variable value. Well, this is one where I think once we sketch it out, like in the optometrist's office, you can say, oh, okay, yeah, that's sort of obvious. Would you rather a situation where you have, and let's suppose we're trying to find a height-weight relationship, would you rather have people that are 5'8" to 5'9" in your data set? And imagine sort of like, here's the population. Let's go with this color. Let's go with purple. For here's the population of height, weight of California adult males. I'm trying to draw it the same in both cases. Would you want to see only people that are 5'8" to 5'9" in your data set to look at a height weight relationship? And we'll go with seven data points. I tried to draw seven, so that's about seven. If you looked at only in very narrow range of heights, would your height weight relationship be very well estimated? Or would you rather have your 7 data points over a wider range of heights? Okay, so darn it, I'm not a fan of this Apple Pencil right now. Okay, there we go. Would I rather have my 7 data points more spread out? I'm thinking that if the goal is to find a height weight relationship, that one, shoot, anything really could fit through the data pretty well. Whereas, like here, even though there's a wide amount of variability, the spread around the trend line is pretty big. Because I have X's that are sort of pushed out to the edges, we can more precisely know the truth. The spread of the X's, the standard deviation of the X's, really is rather helpful for figuring out the XY relationship. In fact, some people would even say, you shouldn't limit yourself, Steve, to just a random sample of heights. Maybe if you want to know the height weight relationship with a total of 7 individuals, maybe you should choose 1, 2, 3 that are really short, 3 that are really tall, and 1 in the middle. So if I choose one person who's right at the average height, and then 1, 2, 3 here, 1, 2, 3 there, and then 1 sort of middle-ish, I'm going to much more precisely because I forced the X's to the extreme ends. So this is something, if you're designing your own experiment, you can more precisely know a slope, literally, if you have a wider range. This is why when the people go out and measure trees and slopes and stuff like that, you would rather sort of have the two people 100 yards apart to find then the angle, which will allow you to calculate the slope, then be 1 yard apart and do it 100 times, where the little errors are going to add up. You would rather have more precision from the data points farther away uh, because of that. Okay, so I think that walks through the nature of why that equation for the standard error, it depends on n, the spread around the trend line, as well as the spread of the x variables. What do we do with that standard error? Like before, standard errors seem to have these two uses in the context of a confidence interval, and then in the context of a hypothesis test. Let's talk about instead of real estate, because I think that's the lab. Let's talk about our bushels per year. If we got our corn data here, you're saying that the yield goes, it seems like it goes up as the years go by. A slope is a rise over the run. And so I guess we could interpret it as the additional number of bushels you get per extra year of history going by. Let's maybe make it that way. So let's go ahead and look at the slope. We see in two places, here's our linear fit. The yield is like goofy, negative 252. Well, but that corresponds to the year zero, and that happened so long ago. This is just a height that corresponds to what would cause the data to go through the trend line to go through the data. But it says 0.149 times year. So 0.15 is the increase in bushels for a 1 year time period. Or if I wait 10 years, a decade, like 1900 to 1910, it says I should be getting 1.5 more bushels per acre on average. Or if I wait 2 decades, that's 20 years times 0.19, that's two extra bushels because of waiting in time. We can also see down here where it says parameter estimates. Let's skip the ANOVA for now and the summary of fit. In the estimate column, the estimate for the slope of year is 0.149. We see the slope is in that location. We also see the intercept is printed for us. So the estimates column tells us how close, I'm sorry, or tells us the slope, okay? The standard error, that's the number that we could talk about calculating before. That's the standard error number here. Software takes care of that for us. And I guess what we need is really a confidence interval going up and down about 2 for 95% confidence standard errors. Um, you can literally do this inside JMP. You can handle that by hand. You could say, well, 0.149 plus or minus, well, 0.06. 0.06 times 2, that's 0.12. So if I go down 0.12 from 0.15, that's like 0.03. If I go up 0.2, 1.2 from 1.5, that's 0.27. So I'm 95% sure that the true underlying population slope is 0.03 to 0.27. But the software could do the whole thing for you. If you right click in the table itself under columns, you could say turn on my lower and turn on my upper confidence interval. So we said about 0.03 to 0.27, we're 95% sure that the actual underlying population slope beta 1 is in the range 0.03 to 0.27. Yeah, I would estimate an additional 0.15 bushels per year, but I'm 95% sure it's at least 0.03 and also less than 0.27. So there you go. There you go. A confidence interval for the slope. And I'm thinking if the confidence interval for the slope, 95% sure that it doesn't here include zero, that says this slope is non-zero. It's going to be positive. I'm expecting a p-value for a test of the slope would be below 0.05. Literally, our p-value for the test of the slope, 0.0187. Interestingly enough, we see it up here as well. But I'm saying this p-value for a test of the slope, it says if in fact the true trend had a zero slope, if indeed bushels per acre is not increasing, if it's flat across history, the chance of us seeing a slope as steep as this one is about 2%. I would rather believe there's a relationship than believe that I was that unlucky, that I was 2 in 100 unlucky with my data. So let's formally get into that hypothesis test. To do our slope, our hypothesis test here is, darn it, I didn't freaking write this down. So let's write it down. Oh, no, it is right here. Yeah. Our test statistic is the sample slope over the standard error. And in both cases, and I wrote this before for you, but let me write it out again because I think it matters to me. Our hypothesis test has a slope of t. Sorry, our hypothesis test is t, and it's the sample slope compared to the slope according to the null hypothesis. I'm going to call that beta 1 0 over the standard error for our sample slope, the standard error for B1. Okay. So yeah, literally what we're doing in any test statistic is comparing what you see in the data. That's what we see the sample slope looks like compared to, shoot, undo that. Okay, that's clearly not what I wanted to do. I'm going to start over. Okay, so my test statistic T, and let's pick a better color. My test statistic T is our sample slope compared to what I would expect to see if the null were true, 0, and divide through by that standard error for that sample slope. We're really comparing, again, what you did see in the data to what you should have seen, 0, if the null hypothesis were true, divided through by a measure of how precisely our sample slope is as a measure of that underlying population's slope. Okay, so I think that is about where I want to stop, but let's verify. No, right there. Okay, I will conclude with this. This thing that I said would likely be Monday, but we have time to do this and then talk about the residuals. Yeah, let's go back to the residuals. Um, the linear model, we said we needed the epsilons to have certain characteristics. Those characteristics we can investigate with what we will call the residuals, the vertical errors. So our true underlying trend relationship, and let's work with orange here. The truth is orange. That is the truth. On the right-hand side, you have like an X, but everything else is an unknown value because it's a lowercase Greek letter. You don't know the intercept in the population trend line. You don't know the slope of the population trend line. You also don't know any individual's actual epsilon. You can't tell me exactly how many pounds heavier I am than the average adult male who is 5'8.5". If you knew beta 0 and beta 1, and you knew my height and weight, you could calculate epsilon. But I'm saying in general, we don't know epsilon. Okay. But we're going to fit that trend line with purple. My trend line is based on, well, a sample slope B1 and a sample intercept uh, B0. Okay. And it looks as though it's a way of coming up with a predicted weight for someone based on, well, their height. So here's the actual truth in orange. Purple is your fitted truth, your fitted guess of reality. And if I compare those two numbers, yeah, literally y minus y hat, if y minus y hat is how far off I am, that's my error, if you will. I'm going to plug the y in here and the y hat there, and it's got some terms that I could collect. There's the epsilon sort of by itself in the leftmost portion. Okay. Then I've got stuff with x's in it. I'm going to lump them together. So B1 or beta 1 times x minus B1 times x, that's going to be beta 1 minus B1 times x. And the only other terms are, well, the actual beta 0, which is unknown, compared to my estimate of the unknown beta 0, B0. What we've got here is a number which should be close to 0. If my estimate's any good, if my estimate in the sample slope is any good, that should be close to 0. And if my estimate of, I'm sorry, if my estimate of the intercept is any good, that should be close to 0. And if the estimate of the sample slope is also any good at all, that second thing should be close to 0. So it's almost as though we could cross them out approximately. And that means my residual, my vertical error around the trend line, is a good estimate of the underlying epsilon. And those should be normal. And we know from yesterday how to check normality, yeah? Shapiro-Wilk. So you could calculate the residuals and check normality. And it should have equal spread, like we said we needed yesterday. Yesterday we used Levine. We're not going to use Levine right now, but we're going to use a way of checking for equality of spread. And we're going to look for whether there's any trend because we require the epsilons to be equal to 0 on average, no matter what. Well, we're requiring the residuals, therefore, to equal 0 no matter what. So let's show you how I could get that with JMP, and your lab will sort of walk you through doing it yourself. So you fit the regression, and again, that's under analyze, fit y by x, just like before. I would say your yield may depend on the year. I click OK, runs an analysis. I fit that trend line, so fit the line. And now I'm thinking I want to save those vertical errors, those residuals, if you will. It's under save. So under my fitted line, I turn on my red little toggle, that allows me to do things. Save those residuals. That's going to give me a new column here. I've got the yield as depending on the year. Here are the errors I have. Let me graph those residuals. I'm going to graph originally my my y, the yield, against the year. We can see there's a trend line. I'm going to sort of make it straight here. And I'm going to click done and make it like that. Now I'm going to similarly graph with Graph Builder the residual on the y-axis. And I'm going to put along the x-axis year like I did before. And maybe, make that straight. And click done. And I'm going to try and line up my friends here. And make it the same. And what I'm arguing is these two graphs are really about the same. Let's look at my errors around the trend line. Looks like here, we've got our, again, with the Apple Pencil, get used to it. Okay, so let's look on the very right of the graph. We see one error, another, a third. It's like right there, and right there. Over here, we see these three are 1, 2, 3 right there. This guy here is that one. These three or two there are right here. It looks as though they're the same graph, other than to get from the top graph to the lower graph, it's almost as though we took a shearing force and we're pushing down on the right side and pushing up on the left. Not exactly a rotation, but close to a rotation where every one of the x's stays in the exact same column. But relative to the trend line, if I sort of apply the shearing force down on the right and up on the left, I can sort of get the graph to be flat. And the benefit of doing that is if there was originally curvature in the data, we now can clearly see the curvature more easily, I should say. Now, I try to emphasize curvature by drawing a banana. If I hadn't drawn those as curved, you wouldn't necessarily see the bottom graph as curved. Okay. I'm saying the bottom graph more clearly reveals a trend. Let me show you maybe why that's the case. Let's take our vertical scale and horizontal scale and switch them up. I didn't really do much of anything. Those graphs are about the same. But if there is a slope here, and let's even make it worse here, if there is a slope, shoot, there we go. If there's a slope that's pretty steep, let's make it even steeper by making it narrower. It's really hard to see if there's a lack of sort of like if there's any curvature. Whereas here in this graph, I could see the curvature much more easily if there is. So a really steep slope makes it hard to see curvature in the original graph. Plotting the residuals against X will make that easier. Okay, we've hit a 1 o'clock. I'm sorry, can't do any more today, but that's okay. The lab will cover the last little things that you need to do before Monday. So, what I want you to do is to finish up the lab as soon as possible. I didn't have it due before Monday. Turn it in by Monday before class. But you guys know your schedules, and if you need to work over the weekend to get it done, that's fine. I personally would say finish it up tonight and then start to studying before the weekend hits. But that's just me. I don't want to impose me on you. But I'm going to hang out for a little bit. If you got questions, I'll be here for a little bit. And otherwise, enjoy your weekend and we'll see y'all on Monday.
Thank you.
No problem. We'll see you.